Building on what we discussed last time, here is a hue circuit of RGB colors, and we're going to use it to do some subtractive mixing experiments to better understand that idea that I landed on last time, that in subtractive mixing, we have to be careful about what we claim about complementary colors canceling each other out. Let's take an additive primary, green. It's set to multiply, which means it will model for me in a simplified way how subtractive mixing will work. Remember that in RGB, a pure green is a color with two zeros in it, 0 red and 0 blue. And when you multiply anything with 0, you get 0. So not only will magenta cancel to black with green, but so will this violet, and this blue, and this raspberry color, and this red. Because it doesn't matter how much is in the R column or the B column of the other color, if you multiply any 0 green color with green, you get 0, 0, 0, black. What about a non-zero green color, like this azure over here? You get to keep your green but less of it, so a darker green. Same thing with this non-zero green color on this side, orange. It's got a little green in it too. So again, we're left with a darker green. You can actually chart out this pattern like this. Credit to David Briggs, by the way, who demonstrated the patterns we're going to talk about today on his website, huevaluechroma.com. What this pattern is telling us is sort of a summary of everything we just saw. All the 0 green colors across the hue circuit from green all subtract to black. Colors with some green content all sort of collapse to this axis along green. If they contain 100% of green, like full saturation cyan, yellow, chartreuse, then they just collapse to full saturation green. Now, can I rotate this 120 degrees? Does it correctly show the pattern of what happens when we subtractively mix red with all these other colors? Let's find out. All the colors on this side are 0 red colors, so they all subtract to black. And these non-zero red colors will collapse to different shades of red. Is the same true for the third additive primary, blue-violet? Absolutely. Just a note here that this figure is very geometrical, all straight lines and predictable angles, because we're dealing with digital RGB colors, which are all composed of just 3 numbers. With real-world colored filters, of course, things are a bit more complicated, as different materials will transmit or absorb different amounts of wavelengths across the entire visible spectrum. Back to our hue circuit. Now I want to examine with you the pattern that emerges with subtractive primaries. Let's start with yellow. We should already know that the color directly opposite will zero it out to black. Ta-da! But what about that azure? We get a dark green. The 0 blue in the yellow is canceling the blue part of the azure. Same with this cyan and this sort of aqua color. Green just stays green, and chartreuse seems to stay the same too. Let's look at the other side of the circuit. The purple gives me a dull red. Magenta and raspberry are also giving me reds. Definitely sensing a pattern here. Well, here's what it looks like. This shows us that the only path through black is with blue-violet. Otherwise, whatever amount of green on this side or red on this side gets left behind means the paths we travel sort of bend out instead of in toward black, like on the additive pattern. Okay, so if I rotate this 120 degrees, we can check if cyan does the same thing. Yep, black with the complement, greens with everything on this side, dull blues with everything on the other side. The pattern holds here. How about magenta? Yep. So we can generalize and say that in subtractive mixing, additive primaries cancel more hues, all hues that contain 0 of that primary. Subtractive primaries cancel only one hue, their additive complement. All other subtractions will have a bias toward one of the 2 additive primaries that are present in the subtractive primary we're talking about. Okay, now my favorite part. Here is the bizarre pattern for a color that is neither a subtractive nor an additive primary, an in-between color. We're focused on orange here. What's the only color that will cancel orange to black? Not its complement, but rather the nearest additive primary to its complement. Its additive complement, azure, will actually mix with it to make a dark green. This straight line, which is analogous to the complementary axis of a subtractive color, if that makes sense, I'm going to call it the subtractive axis, is aimed at purple. Everything on the other side of it will subtractively mix with orange to create red, its closest additive primary. This other line I'm going to call orange's additive axis. The colors connecting to the end of it will all mix with orange to a dark green, the second closest additive primary to orange, and the colors on the other side of it will approach orange in purity. Finally, this pattern is chiral. Only orange, violet, and aqua have subtractive patterns facing this way. Rose, azure, and chartreuse have subtractive patterns facing the other way. You can remember which group these in-between colors belong to based on whether they lie on each other's additive and subtractive axes. Or more simply put, they form two triangles. These patterns are worth getting to know because the same basic logic influences the way paints mix as well.